Okay, so we look at this topic which is on Jacobian control, and in the first, these 3 lectures we will look at Jacobian control of planar manipulators, and we'll study issues and other things that we can do with that. And then subsequently in the course we will figure out how to derive the Jacobian for the spatial manipulators. And while doing the planar manipulators, I will tell you what is the problem with deriving it for spatial manipulators, and then why we need better methods, and proceed according to that. So this is for information for PTL. Now we will start by looking at a 2-link manipulator. So we take this position P at the end of the manipulator, and so as we change the motor angles at theta 1 and theta 2 and move the manipulator around, okay, this point P will change, right. So this point P has 2 degrees of freedom. The manipulator, there are 2 joints, each has a single degree of freedom. So you would expect, or you already know that there has to be a mapping between these 2, right, and we already derived essentially the forward kinematics, which is extremely simple, that Px is equal to L1 cos theta 1 and plus L2 cosine of theta 1 plus theta 2, especially if I have used the right kind of coordinate system and I am measuring theta 2 from here. Okay. Even though this is obvious or intuitively obvious, it is more common is to measure theta 2, or the tendency is to measure theta 2 from the horizontal. If you do that, life becomes very messy. Okay. So we measure theta 2 from the line joining the first axis, second axis, so called common normal in the plane. We measure theta 2 from there. So please make a point of it. Yeah?
Why don't you measure it from the horizontal? Can you explain to them?
Because then to track that angle or to use the angle usefully is more of a problem, and you cannot measure it. So to practically measure this angle, what will you do? You will fit encoder, right, which measures the angle, or you will fit a potentiometer and measure the voltage. When you fit these encoders or potentiometers, you cannot have one end of the encoder or potentiometer attached to the horizontal. So one end will be attached to link 1 and one end will be attached to link 2. So you will always measure the angle relative to link 1 and link 2. So that is why you need a measure which is related to link 1 to measure the position of link 2. So it turns out that this using the DH parameter is quite convenient for these purposes. So that is what we use. Okay. So we can then use Px and Py to represent that position, or we can then keep theta x and theta y, and we can relate these 2. So there are 2 coordinate systems. This is called the joint coordinate system, and this is called the Cartesian coordinate system, which describes the end effector position. Now classically we know that a Jacobian relates the differentials in one coordinate system with differentials in another coordinate system, and you would have used it to transform something like Navier-Stokes equation from the Cartesian form to the cylindrical form. All of you have done that somewhere down the line, right? So that is another example of use of a Jacobian. Where else have you used it?
It's used in finite element methods.
It is used in finite element methods to do what?
You're mapping from world coordinates to the element coordinates in 2-dimensional.
Yes, there is mapping from world coordinates to, that's a little bit more difficult inside this thing. Yeah, so it's used in finite elements. So whenever you have coordinate transformations and you use a local coordinate system, right, and the local coordinate system might be translated. Well, translation usually does not change differential equations. Rotation does, and especially if you want to write equations in coordinate systems which are not, in which the 2 axes are not perpendicular. So then you need Jacobians, because then x and y in a coordinate system need not be orthogonal to each other. You can use any two, say for in a plane you can use any two non-collinear axes, and you can describe most equations using that. So they will also involve Jacobians. It's a very old mathematical tool. Okay. So for the tooling manipulator, we first write the position equations, and to get the Jacobians we can simply find out dpx upon dt. dpx upon d theta 1, so this will be minus L1 sin theta 1 okay. So then you take dpx upon d theta 2. Now this one has only one term in there, so L2 sin theta 1 plus theta 2, okay. So dpx upon dt is equal to sin theta 1 plus L2 sin theta 1 plus theta 2 theta 1 dot minus L2 sin theta 2 dot. Okay. So after we have done this, so we can similarly repeat this for, so if you are now interested in dpy upon dt, so that will be L1 cos theta 1 plus L2 cos theta 1 plus theta 2 theta 1 dot okay. So then it is very convenient to bring this to a matrix form where you write down px dot py dot so minus L1 let me cheat s theta 1 minus L2 s theta 1 2 into L2 c theta 1 2 minus, and this one is L1 c theta 1 plus L2 c theta 1 2 c theta 1 2 into theta 1 dot times theta 2 dot, okay. And so this is the Jacobian J. Actually, on second thought, I should have just converted it here, it's not too bad, okay. So this is the Jacobian which relates derivatives in the Cartesian system to derivatives in the joint coordinate systems, okay. So now why do you want to derive that? What we now do is we multiply this side with delta t. Okay. Now note, I am not multiplying with dt, I am multiplying with delta t, which is a finite time difference. I am multiplying this side with a finite time difference. So if I multiply px dot with a finite time difference, what happens when you multiply px dot with a infinite small time difference? You get dpx, right, which is very small. That doesn't help me practically. So here I am getting a finite position difference. Similarly, I am getting a finite angle change. And now note, I am making this an approximate relationship now. Now why is this approximate? Even though multiplying with delta t, see when I multiply both sides with delta t, that there is no approximation there. I am just multiplying it by a quantity, right? But when I deal with delta px or I deal with delta theta 1, which means change of a joint angle. And if you saw the derivation for the Jacobian, that involves theta 1 and theta 2, right? Now obviously this theta 1 and theta 2 have to be evaluated at a position. There is no definition of a theta 1 at two different joint positions, right? So the big question that comes is, what do you do, which Jacobian is this? Is it at position 1, is it at position 2, is it somewhere in between? Okay. And that is when we have trouble. Okay. But we will defer that question as to which Jacobian we are dealing with, and we'll say, okay, we'll take care of that problem later and see how do we use it. So it's very simple now. You multiply with Jacobian inverse on both sides, so you get now delta theta 1, delta theta 2 is equal to Jacobian inverse delta px into delta py. Okay. And now to compute the Jacobian, we only needed forward kinematics, right? Now this equation gives a method of doing inverse kinematics. Now why is that? I am there at a particular location, I want to move to another location. So I can find out what my delta x and delta y is. So I feed it into this, multiply with Jacobian inverse, it will give me an update of the joint angles. How much do I need to move my joint angles? So this is quite useful. Yeah.
What if we have a redundant degree of freedom? In that case, we don't have a square Jacobian.
Big problem. We'll deal with that very soon.
So in this, like you're saying, we know theta 1, theta 2 and px, py for one initial position of the system.
Now we have to know it, well, that's quite easy.
Yeah, at once we have it, all the stuff that we need.
Yeah.
And then we need to take the end effector to say a new position that differs by delta px, delta py.
Yes.
So if we feed delta px, delta py, so the Jacobian will be variable over, if the delta px, delta py is large, the Jacobian will significantly vary over that range.
Yeah.
So if moving from the end effector from a position to the other, do we have to take small bits of delta px, delta py?
We have to usually move in small steps. It's not a one-step operation. Then there will be trouble. Okay. So now when we are dealing with complicated paths like this, right? So the first thing one should understand is that what is this complicated path that I am tracing? Okay, it's a continuous path. Now how do you represent this path? We cannot take infinite number of points on it, and give it as input data. We will do something to represent it. It's either circles, arcs. Okay, so we break it up, or it's a spline, right? So we anyway have to split it up into some finite number of steps, right? That I want to trace this, general path that I'm interested in. Now once I do it, now suppose I was also, even if you're interested in tracing a straight line path, right? Now if I take, say, this endpoint and say this endpoint, and I want to go on a straight line, I take the straight line path, I can do inverse kinematics, find out what is the new joint values, and I move it uniformly. It is not implied that the end effector will move uniformly in a straight path from here to there. right? So I'll have to anyway chop up that path into some number of points, and I expect that it will move in some kind of a wriggly fashion through it, given that the mathematics is so complicated and there are so many sines and cosines in general, right? So I said typically you will get, every time you're multiplying there are 4 terms, so 6 into 4, 24 terms of sine theta, cosine theta, d's, everything thrown in together. So it is quite reasonable to expect that you will use smaller steps, and if you're doing smaller steps, why find out the inverse, why do inverse kinematics? You can use this method to interpolate. So what happens is you get started here. Now suppose your target position was somewhere here, but if you use the Jacobian, you will generally head off in this direction. Now why am I indicating this direction? Because the Jacobian is roughly equivalent to a tangent. If you are moving this side already, it goes along, there's a gradient aspect which is in there, so it will go roughly, let us say it's going along a tangent, so it will end up here. Now if your next target point is say somewhere here, if you again use Jacobian control from here going to here, you will end up somewhere here. You have another target point, maybe here, you will end up here, next target point is here, you will end up on the top, so you will go on both sides of the line. You may go to both sides of the line, you may not go to both sides of the line. You might approach a line tangentially also, depending on what the nature of the curve is and so on and so forth. So you will get this structure. Okay. So we will deal with this in more detail after we do some more math.